guys, today we're going to show a quick and easy process for finding the prime numbers between 1 and 100. This process is called the sieve of Eratosthenes. Now the name for this process sounds more complicated than it really is. Here's a sieve and here's Eratosthenes. There's nothing complex about the name of this process and nothing complex about the process itself either. What we'll be doing is looking at the numbers from 1 to 100, separating the numbers we need, the primes, from the numbers that we don't need, the composite numbers. Just like a sieve separates two different substances, so you can keep one of the substances and get rid of the other. We keep the primes and get rid of the composites. If, by the way, you don't know the difference between prime numbers and composite numbers, not to worry, you don't really need to know it for today's lesson. But you will need to understand the differences when, in the future, you're working on things like finding lowest common multiples of different numbers or highest common factors of different numbers, and trying to simplify fractions. So in the description box, I've linked to another video that I made which describes how these two types of numbers differ. I recommend you watch that video because it will also help you understand why the sieve of Eratosthenes works in the first place. I'll put an on-screen link at the end of today's lesson so you can watch it after this video for a more detailed look and basic explanation of the prime numbers. So let's get this process started. We'll take the first few prime numbers, 2, 3, 5 and 7, and taking a prime number one by one, we'll eliminate all of their multiples between 1 and 100. By the time we're done, we'll have eliminated every number between 1 and 100 that is not prime. First thing we'll do is eliminate the number 1, because the number 1 is not prime. And if you need to know why, watch the video I've linked to at the end of today's lesson for an explanation. Now, let's take our first prime number, 2. Let's eliminate all multiples of 2. There you go, it's as easy as that. Already, we've gotten rid of almost half of the numbers. These multiples of 2 are not prime. Now let's take the number 3 and eliminate its multiples. Now be careful here, some of the multiples of 3 are also multiples of 2 and you already eliminated those. Some examples are 6, 12, 18 and 24. If you're trying this at home, I would suggest using a table like this and running through your multiples with a straight line like I have. Then you won't have to look for the same multiples more than once. It will save you time. Now let's eliminate the multiples of 5. Well, the numbers ending in 5 are easy to do, but also numbers ending in 0, all the 10s, are multiples of 5, but they've already been done. They were also multiples of 2, so we only have one column to eliminate. I can't stress it enough. You'll need to watch my other video to understand why this process works. Finally, let's eliminate multiples of the prime number 7. Well, several of 7's multiples are already eliminated because they are multiples of other primes smaller than 7. We've only got a few left now, 49, 77 and 91. Now look at the numbers that we have left. None of these are multiples of any of the 4 primes we've already looked at. These are all the prime numbers between 1 and 100. Now you might be tempted to ask, why haven't I tested these other numbers? Well, I'm going to leave you with some experimenting to do, but I'll also give you a clue. On this chart, I've coloured in yellow our only remaining numbers that were not multiples of our original primes. I've given the original prime numbers their same colours as before. Any number which just has the normal white background is a multiple of one of the original primes. And that means that those numbers with the white background are composite. They are not prime because they're multiples of either 2, 3, 5 or 7. Take the number 11 for example. 11 times 2 equals 22, but that's already a multiple of the prime number 2, so it has already been eliminated. 11 times 3 equals 33, but again that's a multiple of the prime 3, so that's been eliminated as well. 11 times 4 equals 44. 44 is a multiple of 2. We've already covered that. If you experiment, you'll see that all multiples of 11 up to 11 times 9 are already covered by the smaller primes, and 11 times 10 is already larger than 100, so you don't need to consider that multiple. All you needed to do was multiply 11 by the first row of numbers, the numbers 1 to 9, and you have covered enough multiples of 11 to cover all the multiples between 1 and 100 and not greater. Try this with the prime number 13 and with 17 and other larger primes. Because they are bigger than 11, at most you'll only be able to multiply them by the numbers in the first row, which means they'll either have to be multiples of 2, 3, 5 or 7, which they cannot be because we already eliminated those and there are no more multiples of those numbers, or they'll be multiples of 4, 6, 8, 9 or 10, and those are either multiples of 2 or 3, and we've covered all of them as well. You won't be eliminating any other numbers from this box. If you don't believe me, give it a try and let me know in the comment section if you manage to eliminate any more of the numbers. So there you have it, how to use Eratosthenes' sieve to find the prime numbers between 1 and 100. I hope you enjoyed the lesson, and don't forget to watch the more detailed and basic explanation of the primes that I'll link here. It'll help you get a better understanding of why this process works. The next video in this series will be on prime factorization, so don't forget to subscribe and hit the notification bell to be alerted when I release the next video. Well, that's it for now. Take care. Until the next video.